Hello, I'm Ahmed Shaban. I'm a P.h.D. candidate at the Department of Physics at NC State University. I'm working with Professor Rongmon Bordoloi. I'm studying spatial resolving galactic outflows using gravitational lensing. So in this project, we would like to quantify the outflows in gravitational lensing galaxies. So before we start, what are the components of a galaxy? So the components of a galaxy, you have a stars and you have a supermassive black hole in the middle that acts like a sort of large gravitational source that everything rotates around it within a galaxy. And also you have cold gas and hot gas. The cold gas is considered like the fuel for star formation, and the hot gas cools with time and turns into cold gas. So it is a dynamic process that evolves over time, and the stars also evolves over time. At the end stages of some of these stars, massive stars, they can explode as a supernova and eject a lot of materials out of the galaxy if they have a high enough velocity to escape the gravitational potential well of the galaxy. This happens in the form of what's called galactic wind or galactic outflow. And we can see this in this figure here, the impact of these outflows. So these outflows can regulate the star formation by slowing it or making it faster, and also they can stop the star formation completely by removing all the cold gas from the galaxy. Also, outflows can carry metals from the interstellar medium of the galaxy to the surrounding intergalactic medium or circumgalactic medium, which is like a faint medium around the galaxy, which consists of gases and other metals. So what are the driving sources of these galactic outflows? So the driving sources can be supernova or stellar winds from OB massive stars, or active galactic nuclei, where you have gas accreting in the supermassive black hole at the center of the galaxy. And this accreting gas ignites nuclear reactions, nuclear explosions that propels a lot of gas out of the galaxy. In my work, I will focus on outflows driven by star formation. What is the importance of these galactic outflows? So without these outflows and other feedback mechanisms within a galaxy, the current cosmological simulations fail to capture the current observed population of galaxies. So they use subgrid recipes and fine-tune the outflow parameters in the simulations to match the observations. The importance of my work is to provide a spatial resolved measurements from observations of high redshift galaxies. This will guide the simulations regarding the outflow velocities, mass outflow rates, and the mass loading factor, and these are very important parameters for simulations. So how to detect these outflows? We can detect them using a spectroscopy, mainly through the emission and absorption lines of different elements and metals, entrained in the hot outflow ejecta. In my work, I use ultraviolet lines from magnesium and iron, mainly singly ionized magnesium, or magnesium-2 in this case, and singly ionized iron 2. They get redshifted from the UV into the optical part of the electromagnetic spectrum, and we can observe them using ground-based telescopes. This redshifting from UV into the optical happens because of the expansion of the universe. It stretches the light to longer wavelengths from UV to optical. So previous literature provides us with like integrated measurements of galaxies, which means you get like one measurement of the outflows within each galaxy in your field of view. So one measurement for each galaxy, because the galaxies at a higher redshift, they are small on the sky, have a small angular size, and also they are very faint. You have to spend a lot of time in order to get spatial resolved measurement of these galaxies, and it is not always feasible. Our method is to use strong gravitational lensing. So the gravitational lensing happens when you have like a massive object, like a galaxy or a galaxy cluster. This massive object can distort the space-time around it, also distorts the null geodesics along which the light travels. So if you have a background source and a foreground massive object, the background source will appear distorted in the sky. It will be magnified and much brighter, and it will be extended as multiple images or extended arc, as we see in the image here. So gravitational lensing acts as a natural telescope that magnifies and stretches these high redshift galaxies shape on the sky. So this provides us with the opportunity to get a spatial resolved measurement of these extended objects on the sky. And especially for outflow, it is quite challenging to observe the outflowing gas directly through emission at a high redshift, as the gas surface brightness is proportional to the square of the number density of the gas. So this makes the emission too faint unless if you have very dense outflowing material. So we can use a gravitational lensing effect that magnifies the galaxy and increases its surface brightness and detects the outflow and emission, and also zoom in and get the properties of the outflows driven by a local star forming region within the galaxy. And for the observation, we use integral field unit spectroscopy. And this instrument provides us with one spectrum for each pixel in the field of view in the same time, as shown in the figure here. So this means that you will have shorter observations time for a larger field of view. And by coupling that with gravitational lensing, we can obtain spatial resolved measurements of outflow properties of a galaxy at a high redshift. And we can probe multiple regions within one galaxy and get the spectroscopic properties of the outflows within each part of this galaxy. For our target galaxy, we have a strongly lensed galaxy at redshift 1.7, and it shows up like as an extended arc in the sky here, which extends around 38 arc seconds, and there is another counter arc at the bottom of the image here, which covers around 7 arc seconds. And this galaxy is lensed because there is a foreground galaxy cluster at redshift 0.56. And the main arc consists of multiple images, which shown here, image 1, image 2, and image 3. And the counter arc represents like a full image of the galaxy on the source plane. The instrument that we are using here is called MUSE, which is abbreviation for the Multi-Unit Spectroscopic Explorer. It is mounted on the Very Large Telescope in Chile, and it has a mirror diameter of 8.2 meters. From these spectroscopic observations from MUSE, we will constrain the outflow velocity, the mass outflow rates, and the mass loading factor, also the spatial extent of this outflow in this galaxy here. And as we said, these parameters are very important for galaxy evolution models and simulations. So this project resulted in 2 papers. The first paper, we quantify the spatial extent of the outflows using the magnesium to emission and iron to emission. So using the magnesium to emission, we detect a 30 kiloparsec spatial extent of the outflow in the source plane of the galaxy at redshift 1.7. And the temperature of this magnesium to gas is around 10,000 Kelvin. And we get this image by tracing the magnesium to emission lines 2796 and 2803 from MUSE observation. And in order to get an idea about the size of this outflow, as we see in this figure, each kiloparsec in this figure represents like 10,000 parsecs, and a parsec is 3.26 light years, which is a massive distance given our human standards. The second result that got published last June. In this paper, we get the outflow properties using the absorption lines, mainly the magnesium 2 and iron 2 absorption lines. Since the galaxy have 4 images at a different magnifications, we use that to probe and dissect the outflow at a different physical sizes. We're going from half kiloparsec square up to 25 kiloparsec square using the main arc images. And in the counter arc, the area is around 60 kiloparsec square. This is the area of the star forming regions here. This gives us the chance to slice and dissect the outflows multiple times over different physical scales, as we can see in this figure here, where the x-axis and the y-axis represent the distance in the source plane, and the bottom layer represent image of the counter arc in the source plane, mainly the star forming region from Hubble Space Telescope image of this galaxy. And second layer represents the apertures that we use for spectral extraction from image 3. And the third layer is image 1, which is less magnified. And the fourth layer in the top represents the apertures from image 2, which is most magnified. So the magnification increases from top to bottom. So we get the properties at the different physical areas and physical scales depending on the size of the apertures that we are using. And from that we get properties like the outflow velocities that is shown on the left panel of this figure here versus area. And as we can see the scale of the areas that we are probing. So the data points which have a similar colors represents the same star forming regions but probed at a different areas in the source plane. And this gives us an idea about these variations depending on the areas that we are probing here. And the red point represents the global measurement from the counter arc. And on the right hand side we get the mass outflow rates, which is very important for simulations. And we get also variations with the area probed here. Also, when we compare our measurements to measurement from previous studies in the literature, like this figure here, where we compare the mass outflow rate on the y-axis versus the star formation rate on the x-axis. Our measurements are shown in blue and cyan circles and squares. And all these measurements are from one galaxy in this work here. And we compare it from 3 other papers where each data point represents one galaxy. And as we can see here, the scatter in our data points is consistent with the literature here, even though our measurements are from one galaxy. The diagonal dashed lines here represent the mass loading factor, which is just the mass outflow rates divided by star formation rates, which is one of the important parameters for simulations. And we can see that for our galaxy, the mass loading factor goes from around 1 up to 10 for the majority of the data points that we have in this work. The scatter in the literature covers a wider range of mass loading factor here. This shows the properties of the outflows in one galaxy, shows a wide range of properties. Our conclusion is that for simulations to capture the real properties of the outflows, you need to take into account the small scale variations within one galaxy as shown with these measurements here. This is the final conclusion of our work. This work will further enhance the current models of galaxy evolutions and simulations. Thank you.